Welcome back to the deep dive. Today, we're diving headfirst into something that silently powers so much of our digital world, often without us even realizing it. Our mission today is to take a stack of pretty dense information on the Linux kernel and distill it down into those surprising facts and, those aha moments that genuinely make you feel well informed. Linux is absolutely everywhere these days, quietly underpinning everything from your smartphone and smart home devices to the colossal servers that run the internet and even supercomputers. But what is it really at its very foundational core? Today, we're stripping back the layers and going deep into its heart, the Linux kernel.
It's fascinating because Linux is a relatively young member of the vast Unix-like operating system family, yet its rise to spectacular popularity starting in the late 1990s was truly meteoric. And by understanding the Linux kernel, we're not just dissecting one operating system, we're also getting a handle on the core concepts and design philosophies that underpin so many modern operating systems you interact with every single day.
Okay, that sets the stage perfectly. So, where did this ubiquitous piece of software even come from? Its origin story is quite remarkable, really. Linux was initially developed by Linus Torvalds back in 1991, primarily as an operating system for IBM-compatible personal computers running on the Intel 8386 microprocessor. And what truly blows my mind is that Linus remains deeply involved today, constantly improving it, ensuring it adapts to new hardware, and coordinating the hundreds, if not thousands, of Linux developers around the world. That's a level of sustained personal commitment you rarely see in such a massive project.
It really is, and it brings us to a common point of confusion, actually. Technically, Linux is a true Unix kernel, but here's the nuance. It's not a full Unix operating system on its own.
Okay, what do you mean by that?
Well, it doesn't automatically come with all the applications you'd expect, like file system utilities, graphical desktops, or even, basic text editors. But the brilliant part is that most of these programs are freely available under the GNU General Public License, or GPL.
Ah, the GPU.
Exactly. This means they can be, and almost always are, easily installed in every Linux-based system, completing that full operating system environment we all recognize.
And for anyone who loves understanding the mechanics of how things work, here's where it gets really interesting. Linux isn't a commercial operating system you buy. Its source code, distributed under that GPL, is completely open and available to anyone to study.
Anyone.
You can literally download the code and explore, from top to bottom, one of the most successful modern operating systems. That transparency isn't just cool for tech geeks, it's incredibly powerful.
It absolutely is. The sources highlight some incredibly compelling advantages Linux offers, which really explain its widespread adoption. First, it's cost-free. You can install a complete Unix system with no expense other than the hardware itself.
Right.
This isn't just about saving a few bucks. Think about the impact of this. It's why Linux powers tiny embedded devices in your smart home, the routers keeping the internet running, and massive server farms devices that simply wouldn't be economical or even possible with heavier commercial operating systems. It's truly enabling technology at a foundational level. Second, it's fully customizable. Thanks to clever compilation options, you can select only the features you truly need for the kernel, stripping out anything unnecessary for your specific use case.
So you can tailor it.
Exactly. And because of the GPL, you're free to read and modify the source code yourself. This level of control is unparalleled. Third, it's remarkably stable, boasting a very low failure rate and minimal system maintenance time.
Which is critical for servers.
Absolutely. Imagine the reliability needed for critical servers or long-running scientific simulations.
Right.
Linux delivers that. And finally, it's very well supported. It's often easier to get patches and updates for Linux than for proprietary systems.
Really? Faster?
Often, yes. Answers to problems frequently appear within hours on newsgroups or mailing lists. Device drivers for new hardware are typically available just weeks after product introduction, often faster than commercial alternatives.
That adaptability and the sheer speed of community support you just described are truly remarkable. It highlights why Linux has become such a cornerstone of modern computing. But all this flexibility and power hinges on one core component, the very heart, you might say. So let's strip back the layers even further. What is a kernel, fundamentally, and how does Linux handle this crucial role? Every computer system includes a basic set of programs called the operating system, and the most important program in that set is the kernel. It's loaded into your computer's RAM when the system first boots up and contains all those critical procedures that are absolutely necessary for the system to operate. So when we talk about the kernel, what are its primary objectives? What's it trying to do?
The kernel has two main overarching objectives. First, it's the gatekeeper that must interact directly with all the hardware components, managing everything from your keyboard and mouse to your hard drive and network card.
All the physical stuff?
Right. Second, and equally important, it provides a consistent, safe execution environment for the applications you run, what we call user programs. Unix-like operating systems like Linux are designed to hide all those messy, low-level hardware details from user applications.
Right.
So if your word processor wants to save a file, it doesn't directly talk to the hard drives. Instead, it has to issue a request to the operating system, which then handles the complex interaction on the program's behalf.
That makes perfect sense for keeping things tidy. And it brings us to a really critical concept: CPU execution modes. Modern CPUs introduce at least two distinct modes. You have user mode, which is a non-privileged mode where your everyday applications run. And then there's kernel mode, a privileged mode exclusively reserved for the kernel. Why is this distinction, enforced by the hardware itself, so vital?
It's absolutely vital for security and stability. User programs in user mode are prevented from directly accessing critical hardware components or arbitrary memory locations.
Like a protective wall.
Yep. Exactly. This acts as a protective barrier, keeping the system stable and secure from, say, a buggy application crashing everything, or a malicious one trying to access sensitive data. And this protection is paramount in multi-user systems. Computers capable of concurrently and independently running several applications for two or more users.
Right.
For this to work safely, these systems need robust authentication, protection against buggy and malicious user programs, and mechanisms to limit resource usage. All these protections fundamentally rely on the CPU's privileged kernel mode.
So, to manage who can do what in a multi-user system, Unix-like systems use the concept of users and groups. Each user gets a private space identified by a unique number called the user ID, or UID.
UID.
And to facilitate sharing without compromising privacy, users also belong to one or more user groups, each identified by a unique user group ID. Files are then associated with a specific group, allowing for incredibly fine-grained access control.
That's right.
For example, the file's owner might have read and write privileges, the group might have read only, and everyone else might be denied access entirely. It's quite granular.
Very. And within this system, there's a very special user account known as root, or super user.
Ah, the famous root.
Indeed. This user can do almost everything on the system, precisely because the operating system does not apply its usual protection mechanisms to them.
Wow.
So, with great power comes great responsibility, right?
Definitely.
This account is typically reserved for system administrators who handle critical tasks like managing user accounts, performing system backups, and upgrading core programs. It's the master key to be used with extreme caution.
The root user sounds like the ultimate power user. That level of control must be incredibly powerful for system administrators. But with great power often comes great responsibility, right? What mechanisms does Linux have in place to prevent accidental catastrophic errors or malicious misuse by someone with root privileges? I mean, it sounds like one wrong command could wipe out a whole system.
That's an excellent point, and it's why system administrators are trained to use root privileges sparingly and only for necessary tasks. Linux, like other Unix systems, relies heavily on strong administrative practices, tools like sudo, for example.
Sudo, yeah, I've used that.
Right. It allows administrators to grant specific users limited root capabilities for specific commands without giving them the full password. Furthermore, robust logging tracks root activities, providing an audit trail. But ultimately, the primary safeguard is the administrator's knowledge and caution.
So, discipline.
Discipline and care, exactly. The system provides the power. The user must exercise discipline.
Okay, so we've got users, we've got groups, we've got protected modes, but when a user fires up an application, say a web browser, how does the kernel actually see and manage that running piece of software? What's its fundamental unit of work?
That brings us to processes. Processes are the fundamental abstraction in all operating systems. You can think of a process as either an instance of a program in execution, or perhaps more precisely, the execution context of a running program.
Execution context. Okay.
Yeah. And it's important to distinguish programs from processes. Several processes can execute the same program concurrently.
Like multiple browser windows.
Exactly. Like multiple people using the same web browser application simultaneously. While the same process can execute several programs sequentially, one after another, as it completes tasks.
And in multi-programming or multi-processing systems, You have several processes that can be active concurrently and contend for system resources, primarily the CPU.
Hmm.
On a single CPU, of course, only one process can actually hold the CPU and make progress at any given moment. This is where an operating system component called the scheduler comes in.
The scheduler, right?
It's the brain that chooses which process gets to use the CPU. Crucially, Unix systems use preemptible processes,
Replicating.
meaning the operating system actively tracks how long each process holds the CPU and periodically activates the scheduler to potentially switch to another process, ensuring fairness and responsiveness.
It prevents one process from hogging everything.
Exactly. So, given all these critical tasks the kernel handles, from hardware interaction to managing processes, how is it actually structured internally? Are all these functions bundled together, or are they more separate?
That's a great question about kernel architecture. Most traditional Unix kernels are monolithic.
Monolithic. Big block of code.
Pretty much, yeah. This means that virtually every kernel layer is deeply integrated into one large kernel program and runs entirely in kernel mode. This is in contrast to microkernel operating systems, which aim for a very small, minimal set of functions within the kernel, with most other operating system functions running as separate system processes.
Okay, so two different philosophies. Where does Linux fit?
Linux, however, cleverly blends these approaches to get the best of both worlds, really. To achieve many of the theoretical advantages of microkernels like modularity and easier portability, without introducing the performance penalties often associated with explicit message passing between layers.
Right, that overhead.
That the Linux kernel offers modules. A module is essentially a piece of code that can be linked to and unlinked from the kernel at runtime.
Like plugins for the kernel.
That's a good way to think about it.
Yeah.
Think of a device driver for your new printer. It's a module. Unlike microkernel layers, though, a module executes directly in kernel mode, just like any other statically linked kernel function.
Ah, so no performance hit there.
Precisely. This offers significant advantages. A more modularized approach for developers, frugal main memory usage, because modules can be loaded only when needed,
Smart.
and virtually no performance penalty once a module is linked. It's a pragmatic and powerful design choice.
That is a really smart hybrid approach. It makes me wonder about how all those processes interact with the actual data on your computer. So let's talk about the Unix file system, which is absolutely central to its design. What makes it so fundamental? At its heart, files are simply information containers, structured as a sequence of bytes. The kernel itself doesn't try to interpret their contents, which gives it incredible flexibility.
It just sees bytes.
Just bytes. What's unique is its tree-structured namespace. All the nodes in this tree, except for the very endpoints or leaves, denote directory names. To find a file, you use a path name. If it starts with a /, it's an absolute path name, meaning it starts from the root directory.
The very top.
If it doesn't, it's a relative path name, starting from your current working directory.
Building on that, the concept of links is fundamental. A file hard link is simply another file name within a directory that points to the same underlying file data.
So two names for the same file.
Essentially, yes. The same file can actually have several hard links in different directories, meaning it appears in multiple places as the exact same file. However, hard links have limitations. You can't create them for directories, and they only work within the same file system.
Ah, okay. Limitations.
Right. To overcome these, soft links, also known as symbolic links, were introduced.
Symbolic links or symlinks?
Exactly. These are short files that contain an arbitrary path name of another file, and they can refer to any file or directory, even non-existent ones, and crucially, across different file systems. They're essentially shortcuts.
Much more flexible. So Unix systems don't just have your regular files and directories, they also have specialized file types, right?
They do.
Some are for interacting with hardware devices like your printer or a USB drive.
Those device files, yeah.
And crucially, others are for processes to communicate with each other, like pipes or sockets, which are foundational to how different programs on your computer can talk to one another.
Yeah, pipes and sockets are key for that inter-process communication.
Yeah.
And when we talk about a file, we're actually talking about two things. Its contents, the actual data you put in it, and its identity card, or metadata.
Metadata.
This ID card is stored in something called an inode. Think of the inode as the file's unique fingerprint.
It's fingerprint, okay.
It tells the system everything important about the file. Its type, who owns it, its permissions, when it was last modified, and most importantly, where its actual data blocks are located on the disk. Without its inode, the system wouldn't know what to do with the file, even if the data was still there. Each file has its own inode, and the file system uses it to identify and manage every piece of information.
So, if a process running in user mode can't directly mess with the hardware, how does it get anything done with files? That's where file handling system calls come in.
System calls, yeah.
Any actual file operation must be performed by the kernel in kernel mode. Think of calls like open, read, write, close, rename, and unlink.
The basic operations.
When your program calls open on a file, the kernel creates an open file object and gives your process a file descriptor. It's worth noting that a file descriptor represents your process's specific interaction with an open file, while the open file object contains the actual data related to that specific interaction. It's how the kernel keeps track of who is doing what with which file.
Keeps it all organized. And it's not just system calls either. Kernel routines can also be activated in other ways. For instance, when the CPU executing a process signals an exception, like an invalid instruction, which might indicate a bug in the program.
Whoops!
Or when a peripheral device issues an interrupt signal to the CPU, perhaps to notify it that an I/O operation, like a disk read, is complete.
Like the disk saying, I'm done.
Exactly. These are all critical ways the kernel springs into action to keep things running smoothly.
So all this process-level action is managed by the kernel through something called a process descriptor. This descriptor is essentially a data structure that holds all the information about the current state of a process.
Everything about it.
When the kernel needs to stop a process's execution, maybe because another process needs the CPU, it saves the current contents of the CPU registers, like the program counter and stack pointer, into this descriptor. This way, when the kernel decides to resume that process, it can simply load those saved values, and the process picks up exactly where it left off. It's like pressing pause and then play later.
Precisely. And what's really fascinating here is that all Unix kernels are reentrant.
Reentrant.
Meaning that several processes might actually be executing in kernel mode at the same time. On a single CPU, only one can truly progress at any given instant, but many can be blocked within kernel mode, waiting for the CPU or for the completion of an I/O operation.
Waiting their turn, essentially.
Right. This capability is incredibly important for improving device throughput and overall system responsiveness. The sequence of instructions executed by the kernel for a system call, exception, or interrupt is called a kernel control path.
Got it. The kernel handles process management through key system calls, too. For instance, fork creates a new child process that's almost an exact copy of its parent.
The fork call, yes. Classic Unix.
And exit is how a process terminates. Now, fork sounds like it could be a massive drain on memory, right? Copying an entire process.
It does sound heavy, yeah.
That's where Linux deploys a genius trick called copy on write.
See, I don't.
Instead of instantly duplicating all the memory pages, it just pretends to, only making actual copies if either the parent or child process tries to change something in that memory.
Super efficient.
It's like sharing a document until one of you actually starts editing, a huge efficiency win that lets fork be incredibly fast and lightweight.
It really is clever. This brings us to zombie processes.
Zombie processes. Sounds spooky.
A little bit.
Right.
This is a special state for terminated processes. It remains until its parent process executes a wait for system call on it, signaling it has collected information about the child, like its exit status, and can finally let it rest.
So the parent needs to acknowledge the child died.
Basically, yes. This raises an important question. What happens if the parent process terminates without issuing that call? The information about the zombie would take up valuable memory slots, essentially digital ghosts consuming resources.
Right, leaking resources.
Exactly. The ingenious solution involves a special system process called init.
The init process, usually process ID 1.
That's the one. When a process terminates and its parent is gone, the kernel makes its children because children of init. This init process then diligently monitors all its children and routinely issues wait for system calls to get rid of all orphan zombies, preventing them from consuming memory.
It cleans up the orphans.
It's essentially the digital orphanage, making sure no process is left behind to rot.
I love that mental image, the digital orphanage. And beyond individual processes, modern Unix systems introduce process groups. This represents a job abstraction.
So like pipeline.
Exactly. For example, if you type L2cell sort more into your shell, the shell creates a process group for those 3 individual processes. This allows the shell to act on them as if they were a single entity. There are also login sessions, which encompass all processes descended from the process that started your working session on a terminal, allowing for things like foreground and background process groups.
Managing collections of processes.
Right. Now, here's where it gets really intricate. Memory management. This is by far the most complex activity in a Unix
Oh,
kernel.
yeah.
The foundation for this complexity is virtual memory, a hugely useful abstraction that acts as a logical layer between an application's memory requests and the hardware's memory management unit, or MMU.
Virtual memory serves many crucial purposes and advantages. Think of virtual memory like an elastic wallet.
An elastic wallet.
Okay. You only have a certain amount of cache, which is your physical RAM, but you can pretend you have far more, only pulling out bills from your bank, which is your disk storage, when you actually need to spend them.
Ah, okay, so it lets you use more memory than you physically have.
Effectively, yes. This lets your computer juggle many applications, even if they collectively demand more memory than you physically have,
Mhm.
by intelligently swapping what's actively needed between RAM and disk. It allows several processes to execute concurrently without interfering with each other's memory, and even allows processes to share a single memory image of a common library, saving resources.
Like sharing code.
Right. The core idea is that when a process uses a virtual address, the kernel and the MMU cooperate to find the actual physical location of that requested memory item, whether it's in RAM or needs to be pulled from disk.
So when we talk about available RAM, it's typically split a few megabytes for the kernel image itself, and the rest is managed by the virtual memory system.
Mm-hmm.
This remaining memory is used for kernel requests, for process requests, and very importantly, to get better performance from disks and other buffered devices by means of caches.
Caching is huge.
So what does this all mean for the kernel? It's a delicate balancing act, especially with memory fragmentation. This is where a memory request might fail, even if there's enough total memory available, but it's not available as one contiguous chunk.
Like having enough space, but it's all broken up.
Exactly, like having enough Lego bricks, but not finding them in the right size pieces to build what you need.
To manage this complex balancing act, the kernel memory allocator, or KMA, is the subsystem that tries to satisfy memory area requests from all parts of the system. A good KMA must be incredibly fast, as it's invoked by critical components like interrupt handlers. It shouldn't waste memory, and crucially, it must try to reduce that memory fragmentation problem.
So it needs to be fast and efficient.
Very much so. Linux's KMA, for instance, uses a clever tiered system. Imagine it like a highly efficient multi-level warehouse for memory blocks. It uses something called a slab allocator on top of a buddy system.
Slab allocator, buddy system, sounds technical.
It is, but the goal is to ensure it's not just fast, but also smart about minimizing wasted space and keeping memory tidy.
One clever memory allocation strategy is demand paging.
Demand paging, yeah.
With demand paging, a process can actually start program execution with none of its pages loaded into physical memory.
0 pages in RAM initially.
Pages are only loaded as it accesses a non-present page, meaning when the program actually tries to use a piece of memory that isn't currently loaded. This applies to memory requested with malloc too. Memory is assigned only when the process generates an exception by trying to refer to those virtual memory addresses. It's truly a just-in-time memory delivery system.
Very efficient for startup. Another critical aspect of memory management is caching, especially for hard disks and other block devices.
Because disks are slow.
Exactly. Hard disks are notoriously slow compared to RAM. So Unix systems have a policy to defer writing to disk as long as possible, aiming to maximize cache hits. This means data that's been read from disk and is no longer actively used by a process might stay in RAM on the off chance it's needed again soon, saving a slow disk access.
The disk cache.
Right. The sync system call, for example, can force all those dirty buffers data that's been modified to cache but not yet written to disk to be written back to the disk immediately.
If you really need to make sure it's saved now.
Precisely.
That makes a lot of sense for performance. Now, we've talked about the kernel, processes, memory, but how does the kernel actually interact with all the physical hardware components of your computer? That's where device drivers come in, right?
Exactly. Device drivers are essentially specialized pieces of code within the kernel that control specific hardware devices.
Your graphics card, your network card.
Keyboards, hard disks, network interfaces, sound cards, you name it. They provide a standardized interface for the rest of the kernel to interact with the device. This approach offers several key advantages. Device-specific code can be neatly encapsulated in its own module.
Back to modules again.
Yep. Vendors can add support for new devices without needing to know the entire kernel source code. And critically, device drivers can often be written as modules that can be dynamically loaded into the kernel without requiring a full system reboot.
So you can plug in a new USB device and it just works, hopefully.
That's the idea. It's incredibly flexible. User programs then interact with these drivers through device files, which are typically found in the dev directory.
Okay, let's unpack this. Implementing a reentrant kernel, where multiple processes might be in kernel mode simultaneously, absolutely requires the use of synchronization.
Synchronization is critical.
The problem is, if a kernel control path is suspended while it's in the middle of modifying a crucial kernel data structure, say, updating a counter or a list, no other path should be allowed to act on that same data structure unless it's in a consistent state. If they do, you end up with race conditions.
Where the outcome depends on who gets there first.
Right. And the interaction of the two control paths could corrupt the stored information. So how do they prevent that chaos?
That's right. Any section of code that must be finished by one process before another process can enter is called a critical region.
Critical region. Makes sense.
To prevent race conditions within these regions, several synchronization techniques are employed. One simple solution, often used in older, non-preemptive Unix kernels, is kernel preemption disabling. Basically, the kernel just can't be interrupted.
Simple, but maybe not efficient.
And not sufficient for multiprocessor systems. Another technique for uniprocessor systems is interrupt disabling, where hardware interrupts are temporarily turned off around critical regions. But again, not sufficient for multiprocessor systems. A widely used and highly effective mechanism in both uniprocessor and multiprocessor systems relies on semaphores.
Semaphores, like traffic lights.
That's a good analogy.
Yeah.
A semaphore is essentially a counter associated with the data structure. It has two atomic methods down, which decreases its value and blocks the process if the value goes below 0
Red light.
and up, which increases the value and reactivates waiting processes.
Green light.
It's like a traffic light for shared resources, ensuring only one process enters the critical region at a time, or a limited number. For very short update times, especially in multiprocessor systems, spin locks are used.
Spin locks.
Unlike semaphores, a spin lock has no process list. When a process finds the lock closed by another, it spins around repeatedly, executing a tight instruction loop until the lock becomes open.
Just keeps checking really fast.
Exactly. This is only useful on systems with multiple CPUs, because on a single CPU system, if the process holding the lock can't proceed, the spinning process would just spin forever, hang in the system.
Ah, okay, so definitely for multi-core systems. This leads to a critical concern in concurrent systems.
Deadlocks.
Deadlocks, yes. The deadly embrace.
These occur, for example, when process P1 gains access to data structure A and process P2 gains access to B, but then P1 waits for B and P2 waits for A. This creates a circular dependency leading to a complete freeze. It's like two cars blocking each other at an intersection. How does Linux avoid this tricky problem?
That's a classic problem in concurrent programming. Linux, to its credit, largely avoids deadlocks by consistently requesting locks in a predefined order.
A strict ordering.
Right. If every process always tries to acquire locks in the same sequence, always lock A before B, for instance, it becomes impossible to form those circular waiting conditions. It's a fundamental design principle for stability. Beyond these internal synchronization mechanisms, Unix signals provide a powerful way for processes to be notified of system events. Signals, right.
These could be asynchronous notifications, like a SIGINT when you press 2-3-Alt-C to interrupt a program,
Interrupt signal.
or synchronous notifications, such as a zigzag-V when a process accesses an invalid memory location, which usually means it's about to crash.
Segmentation fault. Bad news.
Usually. Processes can either ignore the signal or asynchronously execute a specified procedure called a signal handler to respond to it. It's important to note that two signals, sigkill and sigstop, cannot be directly handled or ignored by a process. They're the ultimate commands. Sigkill just terminates it, no questions asked.
The unblockable ones.
Okay.
And finally, processes also need to talk to each other in more complex ways than just signals, which brings us to interprocess communication, or IPC mechanisms. How do they achieve that?
Many Unix kernels have adopted what are known as System V IPC mechanisms. These include dedicated semaphores, not just for locking, but for general counting.
Okay.
Message queues for sending data packets between processes, and shared memory.
Shared memory sounds fast.
It is. These are considered IPC resources that are persistent, meaning they stick around until they're explicitly deallocated. Of these, shared memory provides the fastest way for processes to exchange and share data, as they can directly read from and write to the same memory region.
Minimal overhead.
Exactly. There are also POSIX message queues, which are similar but often offer a much simpler, more modern file-based interface for communication.
Different flavors of IPC. And that wraps up our deep dive into the Linux kernel. From its surprising origin story with Linus Torvalds and its powerful open source philosophy, to its intricate internal workings for managing processes, memory, and hardware. It's truly an incredible piece of engineering.
It really is.
The elegance and sheer prowess required to make such a complex system run so smoothly and be so adaptable is astounding.
It really is. We've explored how Linux, by pragmatically adopting the best features and design choices from many different Unix kernels, and by continuously evolving according to the ideas of its countless designers, stands as a testament to how complex systems can be both powerful and incredibly adaptable, especially under that collaborative open source model.
Mhm.
It's a remarkable journey from source code to a global operating system, proving that collaboration can build something truly resilient and groundbreaking.
So as you go about your day, consider this. Given the immense flexibility and power that comes from a kernel like Linux that's cost-free and fully customizable down to its source code, how might this philosophy continue to shape the future of technology in unexpected ways, even beyond operating systems? Could we see this kind of open, community-driven development transform other complex industries, from biotechnology to manufacturing? Something to think about. Thank you for joining us on this deep dive. Keep learning, keep exploring, and we'll see you next time.